Now let's talk about some operations on matrices and properties of matrices. So let's first talk about transpose. So let's say you have a matrix X and it has a usual notation x11, x12, etc. in the first row. So if I want to define its transpose, then basically what I'm doing is I'm exchanging the rows and columns of the matrix, right? So if you remember the original matrix, now instead of that, what you will get is x11 will remain at the same position, but instead of x12 as the next element in this row, you will get x21 and all the way up to xm1. Okay, and here you will get x1n, and here you will get xmn. Okay, so any particular element xij will become xji. So that's a general way of writing this. So this is assuming that the original x was in R m cross n, so the transpose will be in R n cross m. So it's a useful way of looking at matrices, because sometimes you want to exchange, when we are looking at machine learning, we have samples and their dimensions in rows or columns, and we may want to exchange them. Okay. The next operation that we'll talk about on a matrix is its determinant. Now these determinants are only defined for square matrices. So X has to belong to m cross n. Okay, so let's say you have X that belongs to R2 cross 2. Okay, and let's say X, the elements of X are A, B, C, and D. Okay, then determinant of A is a single number. Okay, and that will be AD minus BC. Okay, it has relation to things such as the eigen analysis of the matrix that we'll talk about in a little bit, and its invertibility. So if the determinant is non-zero, then the matrix is invertible. So it's not only defined for a 2 cross 2 matrix, it's also defined for any m cross m matrix. However, the formula iteratively uses determinants of matrices, sub-matrices of lower order, and you can look it up in any basic math textbook or online notes. This is just a quick revision. The next thing that we'll quickly revise is inverse of a matrix. So let's say there's an invertible matrix. So let's say this matrix X, and we take its product with its inverse. Okay, and the inverse we will denote as raised to the power minus 1. Just like for scalars we have 3 times 3 to the power minus 1 is equal to 1. Similarly here, when we have X times X inverse, we will get an identity matrix, which is basically you will have ones in the diagonal and zeros everywhere else. So how we define this inverse, how we compute this inverse for a simple 2 by 2 matrix, this ABCD, would be that this inverse of A, inverse of X, right, would be 1 divided by the determinant of X, right? So this is also called determinant of X, right? So this is X, not A. And this is the symbol for determinant of X. Okay, and inside now we will change the signs and the order of some of the elements. So we'll have D minus B, and then we'll have minus C and A. So you can see that because of this 1 over the determinant has to be non-zero for this matrix to be invertible. Just like the inverse of 0 does not exist in scalars, similar to that, the inverse of matrices whose determinants is 0 does not exist. And of course there's a definition of inverses for larger order matrices. To take this concept of invertibility further, there's something called a rank of a matrix. So the rank of a matrix is the maximum number of columns or rows that are independent of each other, linearly independent of each other. To give you an example, so let's say you have a matrix, right? So you have a matrix of size, let's say 2 cross 3, right? So let's say this matrix is 1, 2, 3, and then 4, 5, 6. Okay, so this belongs to r to the power 2 by 3. Now here what you can see is that although it has 3 different columns, okay, it has 3 different columns, these 3 columns are not linearly independent of each other. I can express these as a some sort of a linear multiplication, a linear combination of any 2 columns. I can take one column and express it as a linear combination of any other 2 columns. So you can solve this. This is just basically system of linear equations. So if let's say we want to describe this particular column, right, we want to describe this particular column as a linear combination of the other 2. What we have is we have 2 unknowns, and then we have 2 things that we want to predict, and then we can find 2 coefficients, let's say alpha 1 and alpha 2, such that if we multiply the first column with alpha 1 and add it to alpha 2 times the second column, we'll get the third column. So its rank is at most 2. Okay, rank of x is less than equal to min of m and n. These are the 2 dimensions of the matrix. Okay, doesn't matter if it was a 3 by 2 matrix, then also that would be the case. Right? But rank can be even lower than that. So let's take another example where you have another matrix, or let's call it y. Okay, and here let's say this is 1, 2 and 3, and then it is 4 and 8 and 12. Okay, so here the rank is even less. I can simply take one column, and multiply this with alpha equal to 3, and I can get this column. I don't even need the second column. So here the rank is 1. Okay. So keep that in mind, that only the upper bound on the rank is defined by minimum of m and n. It could actually be less than that. In that case, for square matrices, when you have size m times m and the rank is less than m, then these are called rank deficient matrices. Rank deficient. Okay, and for a square matrix, if rank is same as m, okay, so if x belongs to R m cross m and rank is equal to m, then it is called full rank. So only full rank matrices are invertible. Rank deficient matrices are not invertible. So rank deficient matrices are not invertible. Okay. Only full rank matrices are invertible. So you can think of it this way, that in any case, whenever you have matrices that are not square, then they are not invertible. Right? You cannot get you cannot invert them. They are rank deficient anyway. So inverse is anyway defined for square matrices.